Is Matt Kwan, and I'll be presenting our final project for ECE Embedded Systems. This is the Embedded Parking Assist project. So when I start the project, it'll present the test case that it's about to run. So in this case, it's going to set up one obstacle out of the range of the parking assistance sensor, one obstacle within the range, and then one closer in range. And it will do this, it'll do the first two at the same time, and then it'll pause and it'll do the next one. So I'll start the test case, and everything kicks off in real time. And we'll use all these logs to compare with the functional and non-functional requirements. So at a high level, we can see that after the first ping, which is initialization, we get sort of 4 stars away in terms of distance. So this should be the ones that are a little bit further away. And then after the amount of time has passed, you'll see that the closer obstacle was detected, and you get 2 stars here. So that's the basic functionality confirmed. And now let's go one by one through the requirements. So CPU must report all sensors information every 300 milliseconds. So if we count the number of, so this is for one sensor, because there's only one here, we can count the number of milliseconds between messages. So we'll see 80 plus 80 plus 80 plus 80, 1, 2, 3, 4. 4 times 8 is 320. About 300 milliseconds passed here, and the next message came in. Next, sensors must report a proximity every 80 milliseconds, which you saw here because this is timed from the beginning of the function call to the end. Sensors must not use pings that can be spoofed without internal knowledge of the system. No jammer was introduced in this one, so we'll take a look later. The Scrum methodology, and then system must be tested for test cases for 0, 1, and 1 plus obstacles at various distances. Here we did, we checked off 1 obstacle and then 1 plus obstacle at various distances. And then lastly, system must employ a real-time operating system in the CPU to manage deadlines. And here you'll see our round-robin interrupt-driven partial RTOS implemented here. We have 3 tasks. One is to prepare the display, to actually do the display, and to process the sensors. So task 0, 1, and 2. And processing the sensors actually has a 49 millisecond delay out of the 50 millisecond time slice that they receive in order to force the CPU to save and restore context between time slices. So that's why you'll see it go a little bit over here. This is representative of what it might be like on an actual system, because there could be a lot more sort of digital signal processing going on. So you'll see that each of the tasks were given the 50 seconds and took the 50 milliseconds correctly. Okay, and so that was this test where there was 1 obstacle out of range, 1 obstacle in range, and then after a pause, another one closer in range. So at the next test case, I'll hit Y to continue. Let's take a look at the output. So test case 2 had 3 not in range and then 2 in range. So at the beginning, we should be seeing these NAs, and then we should start to see the obstacle come in. So here, this is the first message with all obstacles, and you'll see that they're 2 stars away in terms of distance. So you can see that it is reacting in real time because the obstacles are brought in real time, and you'll see how the system performs with multiple sensors as well. So just like before, you can still see that it produces every 300 milliseconds a new report. So if you count the sensor time, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 times 80 milliseconds divided by 4 is about 300 milliseconds. So let's see, the exact number is 12 times 8 is 960 divided by 3 is about 320 milliseconds here. So 300 milliseconds with the display where it was achieved. Sensors, each of them was reporting 80 milliseconds. You'll see that there's 3 times the number of these messages. And this tests for 0 obstacles in the beginning, followed by multiple obstacles. Great, and so you can see how the CPU scales with multiple sensors. You'll see that the round robin is still adequately covering all the sensors, even with a 49 millisecond out of the 50 millisecond time delay for each sensor. Okay, and so the last test is especially interesting because we introduce a jammer. It does a similar setup to the first test, except a jammer will be pumping false echoes to the sensors at a high frame rate. So from the top, test case 3, 1 out of range, 1 in range, and then 1 closer in range with the jammer. So you can see right away the jammer picks it up, and what the jammer does is it's going to copy the sensor ping's waveform, which is why the key is duplicated, and then it's going to spoof the time of flight back by reading its periodicity and then trying to send it back at that rate. And this is what prior researchers have found is a very effective jamming technique that they weren't able to achieve a countermeasure for one sensor. And so something they didn't account for is what if the sent pings are changed. So here you'll see that the pings that the sensor sends out varies. So here it was at a 2.5 amplitude, and at the next ping, it was also 2.5, and then here in this ping it was 4.5. And so it varies between a lower bound and an upper bound. And jammers will not be able to understand how much amplitude that a sensor has sent it out, especially if it's randomized, because it doesn't know how much the signal has attenuated. Only the sensor knows. So the jammer responds with the same amplitude over and over, and that's how the sensor is able to ignore suspicious echoes. Echoes will never return with a higher amplitude than its source signal was emitted from. So it does that comparison as one of the checks to validate an echo. So even with the sensor being jammed, the CPU and the sensors still were able to keep pace. You'll see that the jammer comes out every 20 milliseconds, but the CPU tasks stay at 50 milliseconds each, and the sensors tasks stay at 80 milliseconds each. And displays still occur every 300 milliseconds. You can see the final result where one is out of range and one is in range, and so it'll detect the one in range, and then it'll detect the one closer in range. So after initialization, you have 4 stars, and then it comes in range and should stay at 2 stars. 2 stars. Right, so that's Embedded Parking Assist project for embedded systems. My name is Matt Kwan. Thank you so much.